All right, good morning, class. This is lesson 12. We are covering section 3.2. So this is lesson 12, section 3.2. This is the lecture for July 24th. This is also going to be in connection with today's participation question. Participation day, I believe it's day 11. If you look in Canvas, let's see. Assignments, participation. Participation day 11. Right. So today we're continuing in chapter 3, talking more about determinants. 3.1, we began the process of studying like how we can take determinants of these larger matrices using that cofactor expansion method where you pick your favorite row, pick your favorite column, you go across the row or column, and you're taking each entry and multiplying it by its corresponding submatrix. That's called the cofactor expansion method. So that will work in general, but we've seen, that works really well if like it's not too big, like a 3 by 3, that's not too bad, right? But what if it's a 4 by 4 or a 5 by 5 and there aren't a lot of zeros, right? We've seen that if there's a row or column with a bunch of zeros, and the calculation can be very simple, and we might only have one submatrix to deal with. But if you don't have all those zeros, then if we're talking about a 4 by 4, that means there are 4 different 3 by 3 submatrices you would have to calculate for, and that can become kind of messy very quickly. So what do we do in that situation if it's a 4 by 4 that's not so well behaved? Well, first, we want to highlight other properties of determinants and how modifying the matrix can modify the determinant as well. So we briefly talked about that sometimes you can swap a row, and that's fine. It's not going to change anything. You can look at different things. But sometimes swapping rows can change things. So for example, first of all, we're going to be building a new theorem over here. This theorem is just going to highlight how different kinds of modifications to a matrix, how is that going to affect the determinant? So let's say that my matrix A is 1, 2, 3, 4, right? And we already know we can calculate this determinant using that formula we have for a 2 by 2. Using the formula we have for a 2 by 2, the determinant here is 4 minus 6, or in other words, -2. Okay, but what if I swap the rows? Now, yesterday we weren't exactly swapping rows. We were just saying, what if I use a different row for my cofactor expansion? What if I expand across a different row that has more zeros? We can do that as long as you keep track of the checkerboard pattern, right? But if I swap the two rows, I'm going to create a new matrix, B, which is 3, 4, 1, 2. And now we're going to get a determinant of 6 minus 4, which equals +2. In other words, what happened? Swapping the rows of A flipped the sign of the determinant. So this is going to be our first note here. So first of all, this is for any square matrices. Let A be a square matrix. All right, so number 1. If 2 rows are swapped, I'm running out of space. Let me make sure that's still on the board. We're still on the screen. Okay, good. Oh, that's kind of small. I'll have to write a little bit bigger. All right. If 2 rows are swapped in A to form B, then what happens? Then the determinant of B is going to have the opposite sign of whatever the original determinant was. It's still going to be the same number, but we're going to have to flip the sign, right? So this first thing points out that sometimes, when we do row reduction, we might swap rows. Well, if you swap rows, it's okay to do that, but you just have to keep track of each time you swap rows, it's going to be flipping your sign. So if you're trying to figure out the determinant of the original matrix before you swap things, you're going to have to flip the sign of your final answer. And we'll do some examples of this to really highlight this in a moment. All right, so this is the first thing we can do. Great. What happens if I add a multiple of a row to another row? All right, well, let's suppose, again, we're staying with this 2 by 2 case. Try to make it a little easy on ourselves. Let's say A is 1, 2, 2, 5, right? Now, again, this is a 2 by 2, so we already know what the determinant is. We can use our formula for a 2 by 2, and we know our answer is 5 minus 4. We get an answer of 1. But now what if I row reduce this? I'm going to modify row 2, and I'm going to subtract from row 2 times row 1. All right. Well, then I'm going to have 1, 2, 0, 1. And now let's say this is my matrix B. Well, the determinant of this new matrix is still just 1 minus 0, right? So in fact, this is one reason why we really like just basic row reduction. Basic row reduction does not change the determinant. But we do have to be careful about if you swap rows, that could change things. But also notice what I'm doing here. I'm not multiplying the row I'm modifying, right? Row 2 is not being multiplied by anything. Alternatively, I've seen some people say, I've seen this in the homeworks, a little bit on the midterm, how you choose to reduce a matrix does kind of matter now that we're talking about determinants. Some people might instead say, well, I want to take 1/2 of row 2 and then subtract row 1 from it. That'll get me a 0 here. And sure, this is a row reduction you could do, but notice what happens. I get my 0 there, but now I have a half of 5 is 2.5 minus 2. I now got 0.5. What happened? This new matrix now has a determinant of 1/2. This row operation changed the determinant, while this row operation did not change the determinant. What's the difference? Well, when I took this 1/2 of row 2, what you're actually doing in this middle step is you're changing row 2 altogether by scaling it, right? You're applying a scalar of 1/2 to row 2, and then you're adding a multiple to get here, right? So when you do this kind of row operation, this isn't just a row operation. You're scaling a row and then doing an operation. Whereas with this row operation, I'm not scaling a row. It's true I'm multiplying row 1 by -2, but I'm not modifying row 1 with that modifier, with that scalar. Whereas if I write it this way, I changed row 2 with this 1/2 scalar. So the point I'm getting at is that this kind of row operation is good and safe. I'm not applying any scalar to the row I'm modifying, right? But if you apply a scalar to the row you're modifying, that's not just a basic row operation, right? That's not just a basic row operation because you're changing that row. You see how we ended up with a 1/2 here because we multiplied 5 by 1/2? Whereas here, we don't have any fractions up here because there were no scalars that stuck around. So this is a distinction we want to highlight here. So option 2 here, if adding a multiple of a row to another row in A forms B, then the determinants don't change. The determinant of B equals the determinant of A, right? Which is exactly what this is doing up here. I'm adding a multiple of row 1 to row 2. I'm not scaling row 2. I'm not scaling row 1, right? Row 1 didn't change. Row 1 was not scaled by -2. Rather, I just added a multiple of row 1 to row 2 without scaling either. And so that kind of row operation doesn't change the determinant. But if you take the row you're modifying and you scale it with something, you're actually changing it along the way. This is not a basic row operation. This kind of row operation will change your determinant. In fact, this last example kind of highlights the third case of, well, what happens if you, factor out something for a row, or maybe there's some common multiple in a row and you want to simplify it. If you multiply a row by a scalar or you factor out something, it's going to change the overall determinant. So this highlights that, but let's also see it with another example. So consider, let's see, let's think about this example. Let's let A be the matrix 1, 2, 3, 6. Now again, I'm using 2 by 2s, and I'm doing this on purpose because we already have a formula for 2 by 2s, so it's easy to find the determinant. But if we move on to 3 by 3s or 4 by 4s, we can remember these tricks we're writing down to remember how the determinant is going to change. All right, so what's our determinant then for the matrix A? We're going to have 6 minus 6. Oh, you know what? Well, no, that's fine. We're going to get a determinant of 0. Actually, this is a bad example. If they're both 0, it's not a... Hold on, let me change this a little bit. Let me make this 3, 9. All right, the matrix A is now 1, 2, 3, 9. All right. Now what's our determinant? Well, now our determinant is 9 minus 6. We get a determinant of 3. Okay. But maybe you're working through this and you notice, well, hey, wait a moment. Row 2 has a common factor of 3. What if I factor out 3? What happens? So let's take row 2. And I'm going to factor out a 3 by multiplying it by 1/3. This is my new matrix B. We have 1, 2, 1, 3, right? Because 3 divided by 3 is 1, 9 divided by 3 is 3. But now what happened to our determinant? Here, the determinant of B is going to be 3 minus 2. It's now 1. So what happens when you factor something out of a row? Or in other words, the point here is if you apply any kind of scalar to a row, this is why in the last example that applying that scalar of 1/2 to row 2 and changing row 2 like that modified the determinant. The same thing happens here. If I factor out a 3, then my determinant of the new matrix is going to be smaller by that factor. In other words, if I factor out a 3, or in other words, I multiplied A by 1/3, or one of the rows of A by 1/3, what happened here is that my new determinant for the smaller matrix with a smaller row, it's going to be whatever the original matrix was with that factor I pulled out, right? It shrank in size. So this highlights a third point. So here's point number 3. If, and there's a typo in the lecture notes here, but we'll clarify it here now in the video. If a row in A is multiplied by some constant c by c to form b, then the determinant of b equals that constant times the original determinant. So if you factor something out, you have to multiply in order to get that piece back, right? In other words, if you look back at the example we were doing here, if you were trying to find the determinant of the original matrix, you would have to multiply by the determinant of b times 3 to get to the original determinant, right? In other words, whatever you factor out, you need to multiply back in if you're trying to find a determinant of the original guy. Okay? And we'll do some examples of this next. So let's do some examples. I'm going to erase this, but you want to remember this key thing. If you factor something out, then you're trying to find the determinant of the original matrix, you have to multiply it back in order to get the new determinant, or in order to get the original determinant, because the determinant of your modified matrix, it's going to shrink. But if you're trying to find the determinant of the original matrix, well, then you have to reapply whatever you factored to get back to the original determinant. Okay, so what does this look like? We can also highlight here, though, that sometimes, yeah, these rules can be a little confusing to remember. How can we deal with that? How can we avoid this kind of problem? Well, notice, so long as you only use number 2 here, so long as you only are doing these simple row operations where you're adding a multiple of a row to another row, it never changes the determinant. So if you're only doing these kind of row operations, nothing changes, and you don't have to remember any complicated rule. It's only if you do one of these other matrix modifications that you have to be more careful. All right, so let's see an example. Yeah, this will be a good one to think about. So what I'm going to put on the board is slightly different than the example that's in Canvas or in the lecture notes, but they're going to serve the same purpose here. So let's let A now equal a 3 by 3, 1, -4, 2, -2, 8, -9, -2, 14, 0. So I'm modifying this third row from the example that's in the textbook, that's in the lecture notes. But again, you can use both examples, look at both examples, understand both examples, and it'll work out. All right, so first of all, if you're trying to find the determinant of this matrix, we could use the method we learned yesterday, where you just pick your favorite row or column and then multiply by the determinant of their corresponding submatrices. All right. Now, in this case, we don't have any row or column with a bunch of zeros. We do have this 1 0, but we don't have 2 or 3 zeros like we did yesterday. So, all right, that's okay. Now, before we apply these row operations to try to make the determinant easier, I want to first figure out what is the determinant of this matrix, so we can double check our work to make sure we have the correct answer. I'm going to pick column 3 and do the cofactor expansion. So if I pick column 3, remember the checkerboard pattern, plus minus plus, this is a positive 2 times the determinant of its submatrix minus -9, so I have a plus 9, times the determinant of its submatrix, 1, -4, -2, 14. Let me just make sure I didn't make any mistakes. Yeah, okay, we're good. And there's no plus, or we could add plus 0 times. We don't need to. This is it. All right, so what do we get for our answer? We're going to have 2 times negative 2 times 14 is negative 28. Minus negative 2 times 8 is going to be a negative 16, but a double negative. So plus 16 plus 9 times 14 minus 8. Right? So we have 2 times negative 28 plus 16. Oh, what is that? 4, 8, negative 12. Plus 9 times 14 minus 8. What is that? 6? If I did that correctly. Okay. Negative 24 plus 72. And we're going to get a final answer of, let's see, minus 20, 50, 48. All right. So hold on to this. I'm going to write this up here. The determinant of A we know is 48 by the cofactor expansion. Now, admittedly, this cofactor expansion is not too bad for a 3 by 3, right? But imagine if we hadn't had this 0 here, there'd be one more submatrix to calculate, one more determinant to do, one more thing to add. And so this can be a lot of work. Well, what happens if I try to reduce this matrix first? I want to talk about that, and we want to highlight how these different things, we have to incorporate it into finding our final answer. All right. So we kind of know the answer is supposed to be 48. Now let's try reducing the matrix into something with more zeros to make things nicer for us. All right. So first of all, if I'm trying to row reduce this, that means I want to get a pivot below 1. So long as I'm adding multiples of a row to a row, it doesn't change anything, right? Using rule number 2 here. So I'm going to take row 2. I'm going to modify row 2. I'm not scaling row 2. I'm modifying row 2 by adding a multiple of something else. I'm going to add 2 times row 1. And I'm going to go ahead and do the same thing to row 3. Well, you know what? Actually, let's do this first and see what happens. Well, no. Let's go ahead and do it. I'm flip-flopping. Let's go ahead and do it. So I'm going to modify row 3. Again, I'm going to add a multiple to row 3. I'm not scaling row 3. I'm adding a multiple of a row to another row. So this is using number 2. This isn't going to change anything. So I'm adding 2 times row 1. All right, great. So what happens? Our new matrix is going to be 1, negative 4, 2. We're going to have 0, 0, negative 5. And then we're going to have 0. 2 times negative 4 is negative 8. So when we add, we're going to get positive 6. And then 2 times 2 is 4. So when we add, we get 4. All right, great. So we now have this case of we've got some zeros and a non-zero. If I wanted to, this is generally my recommendation with this kind of problem, instead of trying to get it all the way to echelon form, because if I were to go to echelon form, well, that means I would want to swap row 2, row 3. Now I have to remember rule 1. I got to flip the negative in the end. But if I stop right here, and this is my matrix B, well, so far I've not done anything that changes the determinant. The determinant here is going to be, all right, remember the checkerboard pattern, plus, minus, plus, minus. So I have a minus with the negative 5. That gives me a positive 5 times determinant of its submatrix. And what do we get here? 5 times 6 minus 0. 5 times 6 is 30. Hold on, did I make a mistake here? What happened? What happened? Oh, darn it. This is what happens when you make up an example that doesn't follow the notes. Hold on, something went wrong here. So I guess, I mean, this is a good example that when something does happen, doesn't match, then you want to back up and try and figure out what happened. So let's talk about the process. How do you figure out what went wrong? So first of all, this was the original matrix. We were doing row operations. 2 times row 1, so that's 0. -4 times 2 is -8, 0. 2 times 2 is 4. When we add -5, I add 2, 0. I add -8. That gives me 6. Yep. 2 times 2 is 4. When we add, we get a 4 there. Okay. Positive, negative, so positive 5. 1, -4, 0, 6. 6 minus 0, 5 times 6, 30. Interesting. Okay, this all looks correct. So next, let's think about, maybe I made a mistake when I did this original determinant. So I chose column 3, positive, negative, positive. So that is a 2 times the submatrix, the determinant of the submatrix. Positive, negative, so I have a positive 9 times the submatrix. 1, -4, -2, 14. So we have 2 times negative. Yeah, this must be where I made the mistake then earlier. -2 times 14 is a -28 minus a -16. So that's plus 16 plus 9 times 14 minus 2 times 4 is 8. 2 times, so 28 minus 16. 10, yeah, that's -12. Plus 9 times positive 6. Yeah. Oh, I made an awful mistake here. It's little things. I apologize. You probably saw this mistake earlier when I did 9 times 16. -24 plus 9 times 6 is actually 54, not 72. I don't know why I wrote that earlier. That's where the mistake was. You probably saw that earlier, and you couldn't yell at me or stop me because it's video, so apologies for that. But now we can see what happened, right? Earlier, when I did 9 times 6, I wrote 72. That was my mistake. Okay, but now what happens? We get an answer of 30, and lo and behold, great, they should match, right? So what happened? How did I know something went wrong? Well, because I've only done these basic row operations, it doesn't change the determinant. I should have the same answer for both, and lo and behold, I do have the same answer. But what's nice here? Look, originally when I picked column 3, I had to do this big cofactor expansion. But here, all I did was 2 row operations, basic row operations. And then this one little calculation got me to the determinant instead of doing all of this multiplication, which unfortunately I made a mistake at, right? Whereas this calculation is much easier to do. So this is one example for why we like row reduction in this way, especially if you only do these kind of row operations, it doesn't change the determinant. But what if you kept going? What if you were like, you know what? I'm still trying to reduce this to echelon form. I want to see what happens when I do that. All right, so what happens? So we could continue. And if you're trying to get it into echelon form, you would swap the rows. So that's where we have to be careful. We're swapping rows, which means it's going to flip a sign. So I'm going to swap row 2 and row 3. And we get this new matrix, 1, -4, 2, 0, 6, 4, 0, 0, -5. Now, there is a pattern here I want to highlight, and we're going to talk about this more. In fact, it's going to give us a new theorem in this section. But first of all, what's special about the matrix we've created? It's in echelon form. Remember when we talked about, or no, actually, we haven't talked about this. Never mind. We're going to talk about this in just a moment. All right. Okay. So what happens? I've swapped things. It's now in echelon form. Let's try to do our determinant. In fact, what if we pick column 1? Pick column 1. And this is my new matrix B now. Well, then my determinant of this new matrix is 1 times the determinant of its submatrix. And we're going to get 1 times 6 times -5 is -30. Minus 0, we get -30. So because I swapped the two rows, it flipped the sign of my final answer. So what I'm getting at here is that when you do these other operations, that's fine if you do. But if you do them, you have to remember them. You have to keep track of them to see, okay, how does it change the answer, right? If you're trying to find the determinant of the original matrix, you have to keep track of these little things that you do here, right? If you swap two rows, you got to flip the sign. You have to multiply by a -1. So that means the determinant of the original matrix is -1 times -30 to give us +30, right? And then lastly, just to further highlight, what about this third rule? Well, you could perhaps say, well, what if I keep reducing this matrix and I see, look, row 2, I have a 2 in common with the 6 and 4. I could factor out a 2 from row 2, right? So what's that going to do to my determinant? I'm going to take 1/2 of row 2, trying to simplify the matrix further, and we have 0, 3, 2, 0, 0, -5. So what does this row operation do? Well, now I'll do my determinant again. I'm going to pick column 1, just because that's easy. Then we're going to have the determinant of this new matrix B is going to give us 1 times its submatrix, 3, 2, 0, -5. And we get -15 now as a final answer. But that's half of the original matrix. So when you reduce a matrix into its nice form and you do this kind of operation, you're scaling a row, you have to multiply that factor back in, because when you take it by a half, you're making the determinant smaller by a half. So to get the original determinant, you have to multiply that 2 back in, right? So the determinant of A here, of the original matrix, is 2 times, I need to flip the sign because that's what I did up here. So sometimes if you do multiples of these operations, you might have to correct it multiple times in the very end. You swap rows, and we did a scalar, so I need to do both to correct it. Multiply it by -15 to get the original answer, 30. So you can do these row reduction things to get your matrix into echelon form so that the matrix is nicer. But depending on what kind of row operations you use, it might change the determinant, and you have to keep track of those changes as you go along, right? Here we swap rows, and here we modified a row by factoring out something. So whatever you factor out, we factor out a 2, we have to multiply the 2 back in. Whatever you factor out, you have to multiply back in. But the other point of this example was, instead of trying to go all the way to echelon form, just stop once you've made a bunch of zeros, right? If you can make a bunch of zeros with just using basic row operations, it's not going to change your determinant, and you get the same answer, which we saw earlier, right? So you don't always have to go through all of the work to get all the way to echelon form. right? Only do as much work as you have to, make it easier on yourself, and then that way you don't have to really worry about these other two rules as much. You can just stick with your basic row operations. Okay. Now there is one other piece I want to highlight here, and that's the fact, what was the determinant of this matrix B? Well, what's the pattern here? We have this funny looking matrix where let me just make some room. Okay. We have this interesting looking matrix where we have these numbers down the diagonal, but we have all zeros below the diagonal, right? This is actually a special kind of matrix called a triangular matrix. So, definition, a square matrix is triangular. It's a triangular matrix if it has all zeros below the diagonal, which is what we see in this example, or all zeros above the diagonal. So to be triangular doesn't mean it has to be in exactly this format. If you have all zeros above the diagonal, that's still triangular. The point we're getting at is, why do we call it triangular? Well, because it creates this shape where, and I'll just highlight this here, the only non-zero entries are kind of in this triangle shape, right? We call it triangular because the non-zero entries kind of make a triangle in the matrix. So we call it triangular, right? But what's the point? What's special about these triangular matrices? Well, look at, what was the determinant? For my determinant here, when I chose column 1, my determinant was 1, right, times the determinant of its submatrix, which was 6 times -5. Now then there was -0, so I'm not going to write that. And then we got -30, right? Now, of course, because we swapped two rows, we have to flip the sign to get the original determinant, but I'm not worried about that right now. What I'm trying to highlight is, look at this pattern. When I took this determinant, because of all of the zeros I have below the diagonal, it turns out I end up just multiplying the diagonal. It's 1 times 6 times -5. Well, in fact, this is true for every triangular matrix. So one trick you could use to find a determinant is row reduce your matrix until it's triangular. Once it's triangular, the determinant is just by multiplying your diagonal. So for example, if A is an n by n matrix, and so it looks something like this, where you have something on the first diagonal, something on the second diagonal, something on the third, dot, 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 until you get all the way down to the last entry, which is in the nth row, nth column. All right. And I don't really care what's above it. All I care about is that it's triangular, right? So I'm putting these stars in because it really doesn't matter what's here. But it does matter that I need all zeros below the diagonal, right? I need all zeros below the diagonal. Now, of course, I've drawn this where this is called upper triangular because the triangle is in the upper half of the matrix. But just as easily, we said it could be upper triangular, or lower triangular, right? So this picture, you could flip it around where all the zeros are above the diagonal. It doesn't really matter. The point I'm getting at is, what is the determinant Well, because it's triangular, the determinant is taken just by multiplying the diagonal. Just by multiplying those entries, no matter how big the matrix is. So this can sometimes be a very quick and nice methodology for finding a determinant, right? We can use this here. Now, of course, if you do reduce a matrix to a triangular format, well then, just like we saw in this example, you still want to be careful about remembering and checking, like, hey, did I swap any rows? Did I factor something out that I need to multiply back in? You would still have to multiply by those scalars you pulled out, or multiply by negatives if you swap rows. But you can do that and multiply it on top of the diagonal, just like we do here, right? If I multiply by -1, then I get the correct answer for the original determinant. Okay, great. So we have that example. So there are some additional properties of determinants, and then I want to do maybe one more example for the participation question if we have time. And let me make some more space on the board. We'll remember this theorem. We're going to use this more in a moment, but I just need more space on the board. All right, great. So some additional properties. First of all, taking the transpose of the matrix does not change the determinant. It stays the same, right? How can we see that? Well, let's suppose, I just have some basic matrix A, B, C, D. Right? The transpose of the matrix, rows become columns, columns become rows. So I'm going to have A, B, C, D. But look what happens. What's my determinant? Well, the determinant of the original matrix we know is AD minus BC. What's the determinant of the transpose? We have AD minus BC, right? It doesn't change anything. So taking a transpose is still going to preserve the determinant properties, right? Just as it does for inverses, where we have that relationship with inverses. All right. Now we also have, if you're trying to take the determinant of two things being multiplied. Now, these two things can help you simplify things in the homework for 3.2, so you might want to remember this property here. If you're taking the determinant of two things that are being multiplied, you can pull it apart. This is the determinant of A times the determinant of B, right? You can take each determinant separately and then multiply. You can distribute this determinant over the multiplication, pull them apart. Now, there is a warning here I want to highlight. You cannot distribute the determinant over all operations. For example, if you have the determinant of A plus B, you cannot pull this apart into the determinant of A plus the determinant of B, right? So it's only matrix multiplication that allows us to pull it apart into two separate determinants. But if there's a plus sign, there's nothing you can do about it. You can't pull it apart. This does not work, right? There are examples of this. For the sake of time, I'm not going to go through them. You can see examples of this in the textbook as well. So again, if you have A plus B, you cannot pull this apart. It does not work. If you do this, you will lose points. You will get a wrong answer. So be careful of that. All right, great. So we have these properties. And then lastly, I want to go over one final example. Now, this final example is also talked about step by step in the textbook. If you want to read about it in more detail, this is in section 3.2. And we're going to show an example where we're going to use all of the rules we've learned today. Yeah, here we go. So here is our matrix. 2, -8, 6, 8. And then we have 3, -9, 5, 10. -3, 0, 1, -2, 1, -4, 0, 6. All right. Now, if I'm trying to find the determinant for this 4 by 4, I could do a cofactor expansion. Pick your favorite row, pick your favorite column. But unfortunately, we don't have a lot of zeros, right? I mean, I could pick row 3, I could pick row 4. But if I pick row 4, I would have 3 by 3 submatrices to look at, and I have to find their determinant, so on and so forth. That becomes a very long, messy, tedious process. So instead, we would like to think about, well, what if I try to rewrite this matrix as a triangular matrix and then take its determinant? All right, if I want to get this triangular, I want to get all zeros below the diagonal. Alternatively, again, triangular could also be the case where you have all zeros above the diagonal. It doesn't have to be below. It could be all zeros above the diagonal. But just for the sake of this example, I'm just trying to get it all below because that's the same thing as echelon form. All right. Now, I'd like to get a pivot in this first spot, but I notice with row 1, 2, -8, 6, 8, there's a 2 that's in common. So instead of trying to multiply 2 by some factor and then apply it to other rows, I'm going to go ahead and factor out a 2 from row 1. So factor out 2 from row 1. And you want to make a note of this kind of operation. Why? Because it's going to make the determinant smaller, right? If I factor out a 2, the determinant of the new matrix is going to be half the determinant of the original. So whatever final determinant I get when I continue reducing, I need to make sure, like, oh, I factor out a 2, so I need to multiply that 2 back in. All right, great. So what's this matrix then? We have 1, -4, 3, 4, and the rest of this has not changed. And this is also nice because now that I have a 1 here, it's a little bit easier to see how I need to get zeros below it. Because before, if I was going to try to get zeros below the 2, well, I was going to have to multiply it by 3 halves. And that's going to get messy if I have to do that for each piece. All right, great. I want to get some pivots. And I'm going to do some basic operations. I want to modify row 2. I'm going to take row 2 and subtract 3 times row 1. I'm going to take row 3, and I'm going to add 3 times row 1. And I'm going to take row 4, and I'm going to subtract row 1 from it. So notice these are the basic row operations. Anytime you take a row and you add a multiple of another row to it, that's not going to change anything, right? I'm modifying row 2, row 3, row 4, but I'm not applying any scalars to row 2, row 3, row 4. So it's not going to hurt anything. All right. So what's our new matrix after this step? Well, we're going to have 1, -4, 3, 4. Then we're going to have 0. -4 times -3 is a positive 12. 12 minus 9 is 3. 3 times -3 is -9. We add 5, -4. 4 times -3 is -12. We add -2, right? And then we're going to have times 3 and add, so that's 0. Times 3 and add, -12. Times 3, so -3. or no, sorry, times 3 and add. 3 plus 1 is 4. Oh, there might be a typo in the example that's on the board or in the lecture notes. Hold on, did I copy this right? 1, negative 4, 3, 4. 3, 9, 5, 10. Negative 3, 0, 1, negative 2. 1, negative 4, 0, 6. Yeah, there might be another type in the lecture notes. I apologize for that. What I do on the board here hopefully should be correct. Okay. Now, of course, you can always double check your answer. Any TI-83 or TI-84 does have a determinant button in the calculator that you can use to just quickly calculate the determinant. You can use that to double check if your answer is correct. For the sake of this class, you do have to show your steps for the determinant. You can't just use your calculator to get the answer, but you can use the calculator to double check your answer to make sure it's right. Okay, so I'm taking 3 times row 1 and adding. 1 times 3 is 3. When I add, I get 0. Negative 4 times 3 is negative 12. When I add, I get negative 12. 3 times 3 is 9. Ah, that's what I'm doing. 3 times 3 is 9. When I add 1, I'm supposed to get 10. So the mistake was here on the board. Okay, and you guys probably saw that already. Apologies for that. All right. 3 times 4 is 12. When I subtract 2, 10. All right, great. Now this matches our lecture notes. And then I'm just going to subtract row 1. So 0, 0, negative 3, 2. All right, great. So now we're here. I got a pivot. I'd like to make this a pivot, so I need to get zeros below it. I'm just going to do another basic row operation. I'm going to modify row 3 by taking row 3 and adding 4 times row 2. So row 1 doesn't change. Row 2 doesn't change. Row 3, I'm taking 4 times row 2 and adding. 3 times 4 is 12. So I get 0. Negative 4 times 4 is negative 16. When I add, negative 6. Negative 2 times 4 is negative 8. When we add, we get 2. Hold on, what is this? Oh, they factor, I see. All right, we'll do that later. This is still fine. Yeah, they factor out of 2. We'll do that later. Great. And then we have 0, 0, negative 3, 2. Okay. Now, currently, I'd like to get this last kind of pivot here. But I need to get zeros below the negative 6. Well, instead of multiplying by a half and dealing with the fraction, that gets messy. What else could we do? Well, I got 2 options. One, I could swap the rows, and I have to multiply by a negative. Or I could factor out a 2 from row 3. But again, we want to keep track of, if you factor out something, we're going to have to multiply it back in later. So we need to factor out a 2 from row 3, right? So again, we want to star this, remember this. We're going to come back to those. And now we have 1, negative 4. Oh, it's an awful negative 4. 3, 4, 0, 3, negative 4, negative 2, 0, 0. When I factor out a 2, negative 3, 1, 0, 0, negative 3, 2. And lo and behold, now, very last step, I'm going to modify row 4. I'm going to take row 4 and subtract row 3 from it. And that is going to give me 1, negative 4, 3, 4, 0, 3, negative 4, negative 2, 0, 0, negative 3, 1, 0, 0. And now negative 3 minus negative 3 is 0. 2 minus 1 is 1. Now, according to what we've done, to find the determinant of this matrix, I can just multiply the diagonal, right? But I'm not trying to find the determinant of the original I'm not trying to find the determinant of the new matrix. I'm trying to find the determinant of the original matrix, which means anything I factored out, anything where I swapped rows, I have to now multiply those things back in. If I swapped rows, I have to multiply by a negative. Luckily, I didn't swap rows, so I don't have to worry about that. But I did factor out a 2 twice, which means I have to multiply a 2 back in twice. And now I can take the determinant of this matrix just by multiplying the diagonal. And we're going to have 1 times 3 times negative 3 times 1. Well, 3 times negative 3 is negative 9 times 4 is going to give us a final answer of negative 36. Right? So for a 4x4 like this, sometimes no matter what you do, finding the determinant can be messy. At the end of the day, you can use whatever methodology you like. If you wanted to, yeah, you could have done a cofactor expansion, and then you would have had 3 3x3 submatrices to deal with. Alternatively, you can reduce until you get to a triangular matrix. That can work. But if you do that, you have to keep track of, well, did you factor anything out? Did you swap any rows? If you did either of those two things, you have to multiply those things back into your final answer to make sure you get the determinant for the original matrix, right? So these are things you have to watch out for. All right, let's go ahead and look at today's participation question. This is participation day 11. So I'll go ahead and share my screen. Okay, looks like it's sharing correctly. We're looking at participation day 11 here. So we're told, let A be a 3x3 matrix, and we're already told its determinant is 4. All right. Now, suppose B is a matrix that results from swapping row 1 and row 2 of matrix A. So we swap rows. That automatically means the determinant B has a flipped sign, right? So it's the opposite sign for the determinant of A. All right. And row 3 of matrix B is 3 times row 3 of matrix A. What does that mean? Well, that means B has a row which is bigger. If it has a row which is bigger, then its determinant is bigger. How much bigger? 3 times bigger. So what is the determinant of B? Well, we swapped signs, so it should be negative, but it should also be 3 times bigger. So 3 times 4 is 12. Flip the sign. Our final answer for today is negative 12. So here you can go in and answer. What is the determinant of B? The determinant of B equals negative 12. Why? The sign flipped, and B has a row which is 3 times bigger, so its determinant is 3 times bigger, right? Just like if you factor out a 2, like in our example before, it made the determinant smaller, right? So if you have something which is bigger or smaller, its determinant is going to be bigger or smaller, right? Okay, determinant of B is negative 12. Hit submit. And that's all for today. So we're going to stop the share there. If you have other questions, please let me know. We can talk about it. Otherwise, best of luck. Email me. By all means, please email me. Office hours are also Tuesday and Thursday at 6 p.m. Via the office hour link. I've begun grading some of the midterms. That may take a little bit longer, but I will get those graded. Anyhow, all right, best of luck, and I will see you tomorrow.